Guys, in this video we're going to be discussing matrix addition, scalar multiplication, and subtraction. And I guess one thing I can point out right now is this: you might have noticed that I wrote scalar multiplication before I wrote subtraction. And you might usually think of addition and subtraction as going hand in hand. So that's one thing I wanted to point out right now. It'll manifest itself very, very soon here. So let's start with this. Let's revisit the fact that when we talk about matrices, we often use capital letters to represent them. Okay, so we could have a matrix A and a matrix B, where we say A, B, we could say a matrix C. I just wanted to bring up the fact that we could likewise represent these as elements enclosed in a matrix bracket. So we could say this is lowercase aij in a bracket like this. We could say this is the same thing as calling this matrix A. Simply all we're doing is saying these brackets represent our matrix, and aij represents any individual element that happens to be in the ith row and the jth column. Okay, and so we could likewise represent B here. We'd say lowercase b ij, and as well we could say lowercase c I j. Okay, and so these all would be just as fine to name a matrix. We could also call it a rectangular array. So we'd say, for example, A is the same thing we said as aij, and that's simply the same thing as say this matrix here. We say A11, A22, we got A row 1, column 2, A row 2, column 1, da da da, da da da, da da da, all the way down to A, M, N. Let me fix that. M by N, okay, and actually not M by N. It is M N. What am I thinking? Okay, and so we say A first row, nth column, A mth row, first column. Okay, so here's our somewhat sparse matrix, but we can call it all different things. I just wanted to visit this notation because often, we talk about, say, for example, the equality of matrices. Okay, so let's say consider two matrices, A and B as we've defined them above. Let's consider A plus B. Okay, so the simple fact of the matter is, no, let's not go A plus B. I want to say A equals B. We'll just go with equality. This is true, but if and only if a few things here. So the first thing is this. Two matrices, of course, could be equal or the same thing if and only if they had the same order. Okay, so they have to have the same order. And also this must be true if and only if aij is equal to bij, okay? So in other words, every individual element in some respective row and column has to be the exact same thing as the element that is in the same spot on the other matrix. So for example, if we were to say, okay, so let's say matrix A, and A is a 2 by 2, A11, A22, A21, A22, and we say, hey, guys, this is so equal to 1, 0, negative 2, 3. Then some conclusions could be drawn from this. We could say, well, then it is the case that A11 must be the same thing as 1. Or like A22 has to be the same thing as that 3 that's in the other matrix at the same spot. So easy to solve for. Equality of matrices. It was good to talk about that, seeing as how we just want to get that notation down. Okay, so let's talk about addition. Two matrices, we want to add them together. So if we were to say A plus B, and that's what we're interested in doing, what you get is you get some new matrix where we would just say it's Aij, or the individual element in some spot, plus Bij. In other words, what we're going to do is we're going to add the components of both matrices that are occupying the same locations, okay? Or we're going to add component-wise. So let's go ahead and define a couple of matrices here. We'll say A is some matrix, negative 1, 0, 2, 1. Okay, and we shall let B be equal to, how's about 1, negative 1, 3, 2. Okay, and what we want to do is find A plus B. Simple enough, we can find A plus B. So, we write this in roster notation as, okay, so we get the matrix negative 1, 2, 1, plus, so there's our A, plus 1, 1, negative 1, 3, 2. I know I write my matrices in rows sometimes and then by columns, but here's what we get. We get this new matrix that would just be -1 plus this +1, and give us 0 in this spot, or 2 plus 3, the element in the first row, second column of each matrix, add those, you get 5, okay? 0 plus -1, of course, is -1, and then 1 plus 2 is 3. So simple enough. I mean, matrix addition is pretty elementary, okay? So let's talk about scalar multiplication, okay? So we say that was all addition right there. When it comes to scalar multiplication, it's fair to say that if we took some real number c times our matrix A, so c times A, not dot A, but times A, what you get is some new matrix, okay, some new matrix where you have c times Aij. Simply put, what we're going to say is we distribute, you think about it that way, into a matrix, our scalar, okay? So now I'm not actually going to scalar multiply a matrix. I think you're catching my drift, hopefully. But what I want to do is I want to confront this idea of subtraction that came after scalar multiplication when I wrote it up here. And the reason why is because subtraction of matrices is a lot like subtraction of vectors in that you don't really define subtraction. What you do is you kind of think of it as adding a negative of something, and that's really kind of equivalent in so many senses. So what we'll say is this, subtraction, okay, so there's a scalar multiplication. When it comes to subtraction, A minus B, it is okay to write it like this, but I want to think of it as A plus -1 of B, okay, and that's what we'll essentially do. So why don't we go ahead and find A minus B here. We could write this out. We say, okay, so A minus B be the same thing as -1, 2, 0, 1 is our A matrix. This is a 2 by 2. And we're going to add it on to -1 scaling into 1, 3, 1, 3, -1, 2. And so taking this -1 times everything in here really is just going to change their sign. So I'm going to say, okay, so that goes away. This becomes negative. This is now negative. This is positive now, and this is also negative. And then simply all we're going to do is just do our corresponding matrix addition. So -1 is -2. 2 and -3 is -1. 0 and +1 is 1, and then 1 and -2 is -1. So easy as pie. One thing I do want to mention is this. So what if we were to try to take, say, 1, 0. We'll go really trivial here. So this is a 2 by 1 matrix plus say a column matrix plus a row matrix. 2, 1, 3. And I didn't mean equals, I meant add. But this is a 1 by 3. The fact of the matter is this. It just does not exist. D and E, okay? You cannot do this. It is undefined to try to add two matrices that have different order, okay? So don't do that. Enjoy.